So we discussed the two factors. The first one is the material modeling, and the second one is the geometry and layering. And I also executed the code. This code is given here in this section. Let me go to that section for this code. This is the code which is present in this directory in the LET concept here, right? So I discussed two things. The first one is the material modeling, which is the main aspect in this LET concept, and material modeling basically involve the modulus of elasticity and Poisson ratio, which I mentioned in ABAQUS as well, that you need to define these two aspects if you are using LET theory. The second thing is the geometry and layering. So geometry and layering is also an important aspect if you are studying the LET theory, and it is explicitly mentioned here for each thickness. These are defined. The third one is meshing. So the mesh density is very important when you are studying the LET calculations, and for that you also need to study the Sanvoyant principle theory. So area under the load needs a finer mesh, and we discussed this in the previous lectures to capture the high stress gradients, right? And if you have a rough mesh according to the calculations for LET, that will affect your results. So the question arises, how does the mesh size affect the results in ABAQUS if you are using LET theory? Well, basically LET theory is not like that. If you want to use the LET theory based approach in ABAQUS, you actually need to do the convergence study as well, which are important. So also element types are important. For example, if you are using 4-noded plane strain element for 2D, or C3D8 element, which is 8-node linear break element for 3D. So these element types in the pavement analysis also affect your calculations if you are using a comparative study approach between ABAQUS and LET theory. So another aspect in LET is actually the loads and boundary conditions, and for that I have defined this here, this graph from this code here, right? So what is actually happening here? A load is applied at a distance 0 at this point, and it's calculating the stresses for us, and the stresses are calculating for the LET theory according to the concept of biharmonic function, which is given here. And biharmonic function is the function which is dependent on two parameters. One is the radius, another one is the depth, vertical position. So here it is given. This is rotational symmetry, and for the rest of the parameters, m is the integration parameter, and this is the overall equation which you can study here. If you are studying this code and you look at here, it gives exactly the same results to us, right? If at this point the load is applied, the stresses concentration is high, phi function is high, then we are going to the edges, and with edges the stresses are reducing here. But it's not like that. If you are studying this equation totally depend on these constants in the integration as well. So let's suppose if you extend the radius just like here in this equation, you will notice that there will be a variation in this function, and that variation is due to the radius. So every time you are changing the stresses contours, you will observe that phenomena here. So let me use it here. For example, if I use 0.5 instead of 0.3, let's suppose if I use 3 here. So if I click on run module, it will ask me to save the model before using it. So I will here just save it and run it. It will take some time, and it will show me the interesting phenomena here, which we often observe in the ABAQUS as well when we are plotting the rutting profile along the path or on the surface. So it will take some time. So this is another aspect in this LET theory, and this biharmonic function is actually dependent on these integration parameters, and these integration parameters affect the functions which is basically dependent on R and Z, and it's very interesting phenomena here. Let me show you. You can see here the stresses are high here, then the residual stresses, these are reducing, that increasing and reducing, and so on and so forth. So this is the phenomena which you will observe using this equation, and you will find it very interesting. For example, if I even use 0.3 and I change these constants, for example, if I change these constants and I run the code again, so for this equation, this integration scheme is also controlling the behavior of these stresses in LET theory and these biharmonic equations. So these are, you can see here, these are difficult to guess in the initial calculations. So you have to set some limits, which in my case are unity. And if I run it again, I will get the same old graph that I am using in this concept, which is visible here. And I'm going to show you exactly in the same manner these observations in the simulation. So the fourth aspect that you are studying here is actually the load and boundary conditions. And for loads, this biharmonic function is important. If you are studying LET theory, you will observe the same behavior and phenomena in ABAQUS if you are using a layer system without any kind of results. For example, let's suppose I create another model and I call it purely LET concept, right? And I will save this model here. These are alternates, so let's rename it LET alternate 1 and 2, keep them as it is. Let's go to parts, and in the parts, for example, you are defining this geometry here. So first thing you need to do is you need to click on the part, create a part and a sketch. We need a shell element, and if you are defining a axisymmetric model, right? So and you are doing this option, that will capture the same behavior that we are studying here for the Burmester end layer of elastic structure. So this is purely on kind of you know, a 2D axisymmetric theory model. So what does this actually means? I will try to demonstrate this in results as well, but before that, and then I will discuss this profile as well, just in case if you are studying it here. So let's go to the ABAQUS again and call it, let's say this is n-layer system, right? And this n-layer system, let's suppose I define this n-layer system here in the light of LET theory. What should I need to do here? That's important. So let's suppose I have this 2D system. Let me, before that, let me switch off the grids here and quickly draw the guides for myself. So these are for 0, these are for 0, and these are for 0, right? And let's suppose I draw a guide at a specific distance, and similarly I draw a guide at a specific height. So this is R, right? So this dimension is R and this dimension is Z or Z, right? So from function manager I will try to capture this as in R and I will try to capture this as in Z, right? Right now let's suppose Z is 50, R is 500 mm, and Z is actually how much? Let's say 1000. Let's try it. So it's okay, and let's go back to the limits, and 2000 would be fine in our case. Let's quickly create a box here. I will not add so much details to it, and let's check the function. But before that, let's go to create a coincident constraint here, just in case if we want to coincide them, and keep them here. Sorry. So coincident constraint is causing over constraint problem on this problem. I'm sorry. Let's remove constraint from this one. I'm sorry about the constraints. Let's delete these constraints. Now it's okay. So click on done, and the shell is defined here, right? So now according to LET theory that we are studying here, we should define the material interval of elasticity and Poisson ratio. So for that I will define LET material, right? And I will only define it as an elastic modulus and Poisson ratio. These are assumed material. Right, and it's not an accurate material that I'm using here. This is for visualization purpose only. Then I'm going to define a shell homogeneous section for it, which is LET mat, and I will define it here with a unit thickness, and I will define a set here, this point. Then after that I will go to assembly and generate quickly a uh, instance here. So let's say I want to define the tire page for it. So for which I need a specific distance, and this distance is actually this 2a. So I will assume that this is equal to a, and let's do this. Right, and quickly go to a step module and define a step here, which is going to be LET push. For example, LET push tire load is a step which we are using here. And let's suppose I am defining this step with 0.1 increments. That's okay. Okay. And I'm not taking care of anything else. I need to just go to the introduction module, and here I will create a boundary condition, and this boundary condition is going to be pen boundary condition, and it's a displacement rotation. I should consider displacement rotation. So U1, U2, UR3 should be 0. Right? This is because it's considering these layers as an infinite layer when it is treating these layers. I have another boundary condition which should be axisymmetric condition, and this is going to be in this pattern. So this is axisymmetric model, and I will define a pressure of 1, which is going to be a load. So let's call it tire push, right? And sorry about the weird names that we are using here. Let's call it 1, and it is the same air distance which we are trying to discuss here. So let's come back to this model. Let's go to mesh, and inside the mesh, let's mesh it quickly before discussing anything else here. In the previous video, I mentioned that the mesh density is important, and area under the load actually need to be finer as compared to the area away from the load. So for that, there is a very good approach. Let's say we are studying this region, so let's call it minimum size 1, apply to see what is happening here, and let's flip this. So 1 is a smaller value. Let's suppose this is 10 here. So instead of 1, it should be 5. 5 is okay, and okay, so we should consider 5 here. 5 is too much. 10 would be fine, and that's okay, right? Click on OK. Similarly, I should do the same thing for the bottom edge. That should be no, I should keep it as it is, and I should define a value of 10 to these regions only. So this should be single. 10 would be from start, and 100 would be bottom. And let's flip biases for these two. We can apply. So 10 and 100. Then we got this meshing technique here. And similarly for this one, I need a mesh of from 10 to something like this. It's done. And now let's just mesh it to see. The mesh is not bad, but we need to define the same mesh pattern for this region as well. So click on flip, apply, OK, yes, and mesh again. Again, we need the mesh seeding for this region as well. Sometimes it automatically generate mesh seeds, but right now it's not recognizing it, so it's okay now. And we can control the top region here as well. For example, if we select these edges and we click on apply and click on OK. So let's say we try to remesh it. So it's okay, it's fine now. So this is something we discussed in the previous video. And let's go to the job quickly to create a test job. Let's delete this one. Create a test job for LET concept. Right. And in this LET concept, I will first try to apply a data check. If there is something wrong, we could rectify that mistake. And if there is nothing wrong, we are going to discuss this biharmonic function in terms of this equation. It's present here. This is a biharmonic function. It's equation 1. So if there is something wrong, we will modify that, and after that we are going to discuss that. So it's not that much difficult to consider these concepts in your discussion. I think it's very easy to follow these concepts. I do a lot of mistakes, so that's why data check is important. And in the meanwhile, I will try to discuss the other parts, right? So let's go back to our discussion. Let's click on monitor and see what's going on here. So the fourth important point which I want to focus is the loading and boundary condition. So when we are dealing with the tire loads, we either classify it as a static load or as a dynamic load. So the load is based on its nature classified, and when we are trying to study the LET concept, I think I have defined the wrong element 5. Okay, let's go to mesh. Yes. Okay. So let's go to this view. Come back to the purely LET concept. Click on the part, click on edit, convert it to 2D planar. Because our unit system is the same, so let's go to loads again, and before load let's go to property. So I think section is assigned and inspect properly, so let's go to job and again apply a data check here, and let's monitor it. So I was discussing the loads in boundary conditions. So if you are using LET, maybe it's static as per my concept. Again, if properties are not defined correctly, so I will check that again. The LET theory is actually based on this concept of avoiding these complexities. So it's a very basic thing. So let me create another section and call it LET Mate 2 or solid base homogeneous section, and it should be solid homogeneous. Let me delete this, rename this again, click on OK, and let's quickly apply the data check again. Okay. So if you focus on this LET theory, there is a term here R, this term. This R term is telling us that if you are doing an idealization, we actually need to apply a uniform pressure over a circular area, right? So if you are using boundary conditions and based on the LST concept, so the bottom of the sample should be encasted, and the side might be roller supports, which I discussed about the axis of symmetry. But in reality, pavement extends far beyond the loaded area. So using infinite elements or viscous boundary conditions to simulate a semi-infinite space or truncate the model with sufficient distance to minimize the boundary effects. This is the point which is actually bringing our focus toward the limitations of the LET concept. Another thing which is actually important is the analysis step. If you are studying the LET theory, a static general step for linear elastic analysis is okay. And since it's linear, the solution is straightforward. No need for multiple increments. But if there are multiple loads or moving loads, maybe different steps are involved. However, LET typically handle static steps because of the nature of the material definition. So for dynamic or moving loads or viscoelastic or elastoplastic models, these models might be more appropriate if we are talking about LET theory and its limitation inside ABAQUS. So that's why you need to consider the analysis pattern in nature as well. The sixth point, which actually I'm trying to bring your attention toward it, is the comparison of the FEA results with analytical solutions. So it's like Boseniuk or Burmester layer theory. For example, Burmester solution for stress is layered system, and it can be used to check the ABAQUS model accuracy. However, if you are doing any other more detailed and advanced topic with instructions, etc., it will not capture their behavior for you. So that's it. Regarding the degree of freedom 6, it's, I think, related to the rotation UR3, I think so. Anyhow, we can continue this, and let's look at the monitor job here. We will be seeing the warnings, etc., if those warnings are appearing here, so we should do that. Now, when you do all these steps, the final step which comes handy to you is in ABAQUS, if you are looking at the stress contours. Those are vertical, horizontal, and shear and displacements. All these things are important, and that's why the LET theory here calculate the radial displacement, the vertical displacement, and vertical stresses, radial stresses, and tangential stresses. Similarly, shear stresses. But you should notice that we have these little amount of stresses considerations in each function with small amount of variations here. So if I try to summarize the discussion, we have a lot of potential challenges in considering the LET theory with ABAQUS. So that's why it's important to first understand the concept, and I will in more detail in the next video discuss those as well here. Anyways, as you look at the model here, you can study it further, and you can see what's going on in the model here. So LET here in this research article, if you study this, it's actually focusing on the radius here, and it is telling a radius r is the distance from the elevated point to the vertical coordinate axis of rotational symmetry. So this model should be a rotational symmetrical model. So if you look at the mirror pattern and sweep or extrude, so if we consider 360 degree, right, and click on apply, we can see here we have kind of a rotation model here, and if I change the angle to, let's suppose 1 here, oh sorry, 360, 1 degree, we can now see the effect here, and let's simulate it again here. So this is actually the concept of LET in the very first attempt if you are studying LET. So it is actually a function of radial stresses instead of using any other model here, right? Now let me show you how we got the biharmonic function here and how it's going to help us in understanding of the behavior of this biharmonic function of LET and ABAQUS. So let's quickly go to the stresses profile, and I will draw it in undeformed shape, and then I will go to remove this option, that is the rotation, and I will go to option in common and generate the exterior edges just like this. And when I do this, we can also discuss the radial stresses here as well. These are the one major stresses that we need to consider. And let's quickly create a path here. This should be the radius, and let's generate a plot from these stresses profiles here. I will try my best to perform a scripting series of automation in this course as well. That's what I'm trying to do. Okay. Now that's done. Let's quickly go to path, and inside path let's try plot here. So you can see here this variation. If you notice here, we have maximum stresses here, then the stresses are changing, and then those stresses are dropping here, which I mentioned with you as well. For example, if you try to change this code here, let's suppose I change this to, instead of 0.3, I convert it to 0.5, and I run the simulation again. It's actually trying with this integration to capture that behavior here, which we are actually getting here in ABAQUS. So this LET concept, if you study this LET concept, it's very important to understand the theory behind this LET concept before you are working on ABAQUS environment. And I think the Bessel function and biharmonic function are way too much important before starting working on a LET concept. So now you can see this portion is trimmed here, and let's go back to the code here. We have this y limit. So let's suppose if I, for example, I change this y limit from this region to this region, I can visualize this further right now. So you should remember this code here for the y limits. Let me close this, and let me try this again. But before that, let's go to run this code, and let's see its results. So now you are observing here this pattern, which we are actually observing here in this pattern in these results as well. The direction is changing, and if I change it from 0.5 to, let's suppose 3, and I simulate it, if I simulate this function here, this will also give us a concept here that this integration scheme which we are using here, and it is reducing, this depth is reducing at this region, which we are this stress is reducing here. So this is maximum here, then it has a jump here, then this integration, this can be controlled further with these A, B, C and D constants here. So this concept actually teach us about the stresses profiles that we are using here. So if you are trying to visualize other results will have almost the same concept, right? And the stresses will be higher since we are using the S11, that's the shell component for the first direction, and for the second direction these will be kind of no different, a little bit amount of difference will be present in these model, and S33 will be 0 here because we are using shell element, so it's approximately at these region it is 0 here. So S11 that we are using here, it is more versatile approach here, and if you consider this radius here, and if you consider this LET theory, for example, if I change these constants, these integration constants will cause a lot of difference on the simulation of this code here, which is a biharmonic function visualization here actually, and you can observe here that this modulation is changing here. Let's suppose I want to change this d to 1000, the constant will be causing a little amount of effect on the graph here, and you can see that how it is controlling this deformation here. So let's go back to the original code and let's try to make it 0.3 and bring back those limits here and run this simulation here. So it was an initial approach and LET concept to check the behavior of the flexible pavements before the use of advanced patterns and methodologies inside the sophisticated softwares, and this concept is very beneficial for using LET theories. So we have kind of various functions. The first one is biharmonic function, and I demonstrated this in detail. The second function is actually radial displacement. So I'm going to discuss this radial displacement in the next video. Before that, I will try to discuss the limitations of LET theory if we are using this LET theory in all ABAQUS environment. So let me record that in the next video.